So the next set of slides, they look, parts of it are in the book, but I think 90% it is not probably covered by the book. But we look a little bit under the hood on visualizations, and then we talk about some principles, and you will end up, it tends to kind of click with people, and then you'll see you're going to end up using them the entire semester. So I'll talk about visual structure, briefly about Gestalt, talking about pre-attentive processing, how to kind of keep visualizations truthful, and then how to, even if visualizations that show data accurately may not be excellent. So how to, some principles for graphical excellence. And then towards the end, I'm just going to go to a bunch of visualization examples to show you some interesting ones, either bad or good, or something that it's not necessarily something you run into every day. So the first topic, visual structures, is, I put that engine part there. It's like looking inside of a car engine and trying to figure out if that car is going to work for a teenager to drive or for an elderly person to drive. So all visualizations have these things. They're made of them, but it's not necessarily connected directly to your use. I mean, the fact that you have them and you understand them, it's good, and it's kind of required. But the user experience is not going to be necessarily determined by them. So that, again, I told you that visualization, that's the hard part, because the visualization may be constructed very properly from a point of view of everything is well, coded and it's done, but people may not like it, or it may not help them with their problem, or it may not be that efficient for what they're trying to do. But anyway, that's what kind of trying to look at kind of the what is a visualization made of, if I open up the hood. So we're going to talk about spatial substrate, marks, their properties, and then temporal encoding, which is animation, in other words. So spatial substrate, space is perceptually dominant. If you look at this slide, you kind of see it's squarish, and there's lines in there, and there's a kind of a tidal area. So space is pretty much the first thing you see about a visualization, whether you understand it or not, or whether you realize it or not, but it's how space is organized. Normally, it's decomposed on axes, but there's visualizations that do not have an axis. So for example, if I start drawing circles like that, there's no axis in here. So I'm just drawing them. So things exist more or less floating in space. Other types of visualizations, they kind of have a linear feel, but may not be organized as an axis. Things are just one line of something. But most of the time and not most of the time, but if you have axes, they might be shown or not, and the axis itself may be nominal, ordinal, quantitative. Normally, nominal axes and maybe ordinal, they're going to be implying some sort of an area. So it's going to say from here to here, we're talking about Ford, from here to here, the Chevy, and I don't know, Tesla, whatever. So it's kind of, they're going to look more like something along where you have zones rather than individual points. Now, if the axis is quantitative, it's what you are used to with the axis, so they're going to hit dots and labels and so forth on the axis. The axis themselves can be linear. What I drew here is a linear axis, but they can be other shapes. An example can be a radial axis. If you remember, Nurse Nightingales had a radial axis for the months, so basically each part of the circle was for a different month. And then it also had a linear axis that kind of show in the sides. But part of it was linear. You can have them spiral. I've seen visualizations that have data represented on more or less a spiral axis. And any other variation. So whatever people, the more creative you get, probably the less popular, the less people would understand. You would need more specialized users to understand it. And so that's kind of, most visualizations don't just have one axis on one spiral, they may have other combinations. And here, to increase the utilization of space, and space is actually a premium. You can do really good visualization if you don't have a large screen and lots of pixels. But to increase the this is very common sense, but it's called composition. I have one axis. If I could draw on it here. So I have the y-axis is composed with the x-axis. It's pretty straightforward. But that's the term for it. It's composition. I can represent data that way, putting two axes next to each other. Can be in the three-dimensional space also. Sometimes you see those. This is alignment. Again, this may not be the best visualization for the data. I took it from, we were doing something else. So if you look inside the data, it's not the best for what it represents, but it still shows alignment. So basically here you see IBM, Microsoft. This axis is repeated here. So they are aligned horizontally. They start and end at the same point, and they have the same ticks. This way, this allows me to compare what's here to what is there. So I can have the alignment can happen this way as well. I can have the y-axis that's being aligned. And I can have more than two. I have 3 or 4 or 5. That way I can kind of see more patterns, if that's something. So I'm repeating the axis. One that we already seen, it's called folding. It's really, you have it in every book. When a book hits the end of the row, you go to the next row. So you go to the next one, you go to the next one. That is folding. You take the axis and kind of fold it into pieces. This tarantula is an example of, if you want a horizontal folding. Once I hit the end here, I go back and do it. But it's kind of the same principle. So that allows me, in this case, you can see I can have a lot of kind of almost pixel level, can have lots of lines of code that way. Because code is very linear. Otherwise, it would be really long, and I'll have to scroll through it. I think they still have a scroll bar here. But still, much better than having one long line. Here is recursion. So what happens here, everything takes the entire space. But then right here, I break it down into smaller divisions. Here's another smaller division. Okay, so I kind of divide it once, and I give it works well for hierarchical information, but not only. And then inside, let's say this area here, I also subdivided some more, and even some more. So they call it recursively because I recursively go inside of each of these squares, and if I need to, I split it out some more, I split it out some more, and so forth, each individual one. You can see it here too. This one is split out into smaller pieces. Okay, so it's a recursion. The idea here is I'm trying to use each and every pixel. So kind of the entire visualization is kind of split out into smaller. They all work together to form the bigger picture. This one, it was mentioned in the book, the one that I was talking about spatial, where I took the spatial substrate from. I've never seen this in action, and it's they call it overloading, and you have to use interaction to see it. So what you are looking at right now is time, and weirdly enough, they said this was the paper. I actually read the original paper for this. They said it's stock market data, so that's time. And then I have x1 axis, x1, x2, x3 goes this way, x4 goes up this way, and x5. So really the t, x1 and x2, they reside inside the bigger, they reside inside this area here. So as you move them around, all these surfaces change. So somehow you move them inside that 3D area that is made by x3, x4, x5, the big one. So the small ones change. You can see here, you can leave some of them on, or you can just move it quickly and see how the surface changes. So it's overloading because you cannot see the entire information at the same time. You have to move it. And once you look at some information, you hide what's behind the right one next to it. So basically what you move in here, you move the point here, the corner. So now it fits on this. If you imagine x3 going through here, it fits here on x3, and let's say it fits here on x5, and somewhere there on x4. But you can grab it and move it around. And that kind of, that's the end of spatial substrate. Again, there's spatial substrate is very dominant. Many times, sometimes it's unorganized, sometimes it's organized. It may have areas. And within each area, they may have kind of another spatial substrate metaphor where you use axis or folding, subdivision, recursion, and overload. So those are some of, there's probably more that people are creative. They can come up with more than that. So now that I have the space organized, kind of I know where to place stuff, and by stuff are these marks. So what do I do inside the space? I place marks. And many times, not all, I mean, one way to think about marks is that for each row in my data, I'm going to have one mark. That's not necessarily the case. Sometimes I can combine 10 for every 10 rows, I'm going to put a mark, kind of I can aggregate. But generally, marks tend to correspond to rows in the data. Can be one-to-one and can be one-to-many. So once I figure out my space, then I need to figure out what am I going to put in there. So things that occur in space can be a point, can be lines that I place. It can be an area, can be a volume, or it can be like it was the case here. It can be an isosurface, kind of a 2D surface with kind of a weird shape. But that would be things that I place in space. So visualization typically have many marks. If I'm looking at 100 cities, I may have 100 marks, one for each city, so I can kind of be able to compare. There's two things that I don't know if they're marks or not, but I don't know how to deal with them. But sometimes I have two marks that are linked by a line. So that's what I mean by connectivity. I don't know if that line is supposed to be another mark or it's just a property that connects them. I have mixed feelings one way or the other. I won't be able to. And the other thing that happens with these marks, let's say I have a cube like this. What if I have a smaller one inside of it? Is that part of the same mark or two marks placed inside each other? I don't know. But it shows a little bit of a relationship, just like connectivity. Is that something new or is something kind of built in? So, but generally, like I said, there will be marks and there will be, and now that I have marks, they have properties such as color. And the next three slides will go through, not through the properties, but kind of completely different views on them, almost. So this first one, the authors of this, they were calling them retinal properties because your retina does it, but it's not. Retinal to me is more color-oriented, maybe shape. Position may be retinal or not, but that's something. But the position of an object can show data. So if I have a square and it's right here, it can show me something, especially if there's an axis. Or if the same square, or I have another square here, it has a different data property. So all of these things that I can modify, the position, the shape, the color, the size, all of these form properties of the marks. And they each of them can encode a separate data element, kind of a separate column from my table. And this slide kind of breaks it down into a kind of 4 chart. On the left side, there are things that are deal with space, like the position, size, and orientation of my mark. It doesn't have to be a line. I mean, think about, I can have this cube that it's rotated to the left 30 degrees, so you'll see it kind of be on its side. So that's kind of the left side, and the right side, it has more to do with color, with what's inside the shape, if you want. So they break it down by that, and they also break it down by what they call in that extent and differential. So extent would be something capable of showing quantitative data. Remember, I was telling you that 4 is twice as something, as big, as far away, as tilted than 2. Same thing, 20 is 10 times. So you can kind of see that's what they mean by extent. So the authors here, they basically say that extent can be shown by position, which makes sense, and by size, but not by orientation. I'm not sure I agree with that part on the orientation. And they say that grayscale can show extent, but none of these can show it. Well, obviously, a star and a diamond, they cannot show extent by themselves. It's not like there's 3 times more, but I agree with that. The only thing, maybe texture, but even texture, you can have different patterns inside. So that may not be able to show extent. But density of the texture, maybe. But for the most part, that's one view. So these are different types of properties. Here is another view of this area. Jacques Bertin, remember the French, more or less statistician, but he used visualization a lot. So he breaks it down, whether it can, and again, the first two, I'm not sure. You probably have to read the details. What is it? But basically, association shows if they're similar versus selection shows if they're different. To me, it always feels like if you can see they're similar, you can see they're different. But I don't know. Maybe there's a situation where not. But these two generally correspond to nominal data. These two can show order, so ordinal data, and these two show quantity. So here's what Bertin says. Size can show quantity really well. You can see a bar chart. And by the way, you will hear me say many times, it's hard to beat a bar chart. They're pretty good at what they do. They can let you compare quantities. Size here, he says it can show order. And size can also show differences. You can see that there's these 4 are kind of the same. The one in the middle is different. And again, just saying it like that, you can kind of see they're the same. So I'm not sure why they can show association, but it's possible. Value, and by value here, it looks more like grayscale, what they call grayscale in the other one. Here you say it can show order and nominal data. Texture obviously can show association and differences and order. Color by itself, notice it cannot show order or quantitative data. And orientation and shape. So these two agree on orientation and shape. Okay. Next one, again, completely different view on this. It looks at, rather than say it cannot show it, it looks at which one is the most accurate, which one is the least accurate. And it's only for quantitative data, so only for extent. It's not worried about order or categories, nominal data. Position is the most accurate, and it makes sense. I mean, we use axes to show the position on the axis is pretty accurate. You know exactly where it is. It's labeled and all that. Next would be length. And again, bar chart. That's what you have here. There's a caveat here. You know, bar charts, they're really, and I'll probably talk about it again, but they're really good. I can guesstimate the size because they start on the same, even if it's just a small difference. They start at the same point, so you can kind of see small variations. If they do not start at the same point, so if I'm trying to compare those with this one, which one is bigger? I mean, ignore my imprecise mouse drawing, but it'll get harder to compare if they don't start. They don't have a common starting point. Angle, here they say angle is pretty good at showing. It's kind of in the middle. Area, pretty good at showing that. Volume, not as good as area. And then color and grayscale are the least accurate. That's what these authors figured out. Maybe not them, but they kind of looked at research that other people did and kind of collected it together into one simple chart. So keep that in mind if you want to show quantity. Position is your best and probably the most dominant. Temporal encoding, that's the last part of visualization. So you figure out how your space is organized, you figure out how your marks, what their shape. Some of them may be really simple as a dot, others may be very complex. There may be an entire car where you modify the wheel colors and the colors of the handle. So each city that you present is a different car. So your visualization can show 10 cars, but each with very, very many things that can be different between them. So some of these marks can get really complicated. Others are really simple, just a dot. You have the whole gamut there. So, and then you figure out what your marks properties are, where you place them, how big they are, what are their things that you're going to modify them on each mark. And the final thing is that visualization going to change? Are you going to use time? Sometimes, if you look at, for example, stock market data, time is already part of the data, so it makes sense to take that time component and make an animation of it. So you show the stock market 3 days ago, then you do an animation and you show it 2 days ago, and then you show it today. Obviously, I picked a weekend, but but you understand the idea. And you look back, and each frame of that visualization is a different data point. So time versus time. In a way, it's intuitive. In other ways, it's not, because remember change blindness. If you don't cue changes, if there's lots of changes, people are not going to see them. And especially if you're not animating, if things change suddenly, I have 3,000 dots and suddenly I change them all. You're not going to be able to, if your task would be to look at small changes, you're not going to be able to find them. If your task would be to find big pattern changes, maybe that's a good approach for the visualization. But that would be one example where you do frame by frame and you show the visualization just goes and shows each frame a little bit, each frame a little bit. Again, if you are really smart about it, you can encode it where there's a transition period and things get queued. You kind of start flashing points that will. The other thing we can do with temporal and encode non-temporal data. For example, if I have 3 cities, I may show an animation. First animation shows information about the first city. First frame, second frame of the animation, a second later shows information about the second city. A second later, I see information about the third city. So I don't have to take time to encode time. I can take something else to encode to basically become part of the animation. And sometimes I don't encode any information. So the visualization is animated, yet there is no information. I'm only showing the animations to make visualization better. So I have an example here with a graph that I will have to change my screen to do that. And while this happens, I will copy it. And make sure, okay, we're sharing. And it's only about 3 seconds. Don't worry about, I know there are some nodes that are popping up, but it's a graph, it's visualization of a graph of a network. The thing with the network is that you cannot, there are so many links and you can't tell which link is connected to each node. But once the nodes start moving, they're moving because, not because they're showing information, just to make the links become clearer. See how you can see the connection a little bit better when they start moving. It almost gets a 3D, almost a 3D effect. It's the same links, the same nodes, but once I start moving, it's easier to see than with a stop. I've seen this where they just vibrate the nodes a little bit. They just go back and forth slightly, old nodes, in a vibration motion, and it makes it easier to understand that visualization. So I can use animation not to encode data, but to make the visualization clearer.